Hello everyone, this is a video a bit different from the others because the topic is different. Today we will talk about something a bit complicated called tetration. You see it written here, and we will see how we get there. However, I'll tell you, it won't be a video just about computer science. It won't be a video that concerns just mathematics. There will be things a bit from one and a bit from the other. So let's start with the simplest things. Addition, we all know what addition is. It needs two or more addends. We normally take them from the set of real numbers. In this case, we will see later that we will restrict ourselves to positive real numbers. Multiplication, the second operation we consider, is simply addition repeated multiple times. So the repetition of addition many times with the same addend always takes on a particular character, a particular importance. We call it multiplication. So this is the second operation. The third operation is repeated multiplication. You have already understood the mechanism, so we call it exponentiation or simply power. And it is the product, a series of products, always with the same factor repeated many times. And at this point, if we perform exponentiation repeated many times, what do we get? Here is our tetration, which is called tetration precisely because it is the fourth operation of all. To be honest, it doesn't really have a very widespread or practical use. It's not really useful for much of anything right now. But then again, who knows? Sometimes studying topics that seem useless can actually lead to surprisingly good solutions. Let's remember that in our case, if we use the letter A as an example, we must limit ourselves to considering values of A greater than 0. Because if we want to exponentiate, to have a power with both base and exponent as real numbers, these numbers must be greater than 0. So let's look at a somewhat particular case. Well, you'll see that tetration is just an excuse to talk about some rather strange things. It's not really the only topic of the video. So let's look at this equation, which certainly seems a bit daunting at first glance. X raised to the power of x raised to the power of x to infinity is equal to 2, equal to a number. Obviously, the fact that there are the dots emphasizes the fact that the exponentiations are infinite. Now, how can one deal with an object like this? I show this to my students because it helps us understand that computer science must be studied together with other subjects, right? Especially mathematics. I mean, if someone doesn't have a mathematical foundation, it's difficult to deal with a problem of this kind. Computer science in itself doesn't give us much help with this at this moment if it isn't guided by mathematics. So let's reason. You see, the next step is written in quite large letters down here. How can we reason? We have a series of exponentiations, an infinite series of exponentiations. Let's make an analogy. Imagine we have a set formed by elements that are all the same. For example, numbers, every number, by numbers that are all the same, so the number 1. And this set is an infinite set. If I remove one element from this set, what do I end up with? I get the same set as before with one number removed. However, this removed number must be compared with the fact that the set is infinite. Well, in reality, removing an element, or rather a finite number of elements from an infinite set, does not change, let's say, the set itself. You could say that the set remains the same because if I remove an element from an infinite list, I still get a set that is still infinite. It remains to be seen whether this reasoning is valid or not. Let's try to put it into practice and see what happens. So let's assume that nothing changes. Therefore, let's say the list of exponentiations, removing the first exponentiation, which is precisely why I, let's say, drew it in red, removing the first exponentiation. The whole list, including the dots that indicate to me the fact that it is infinite, is equal to the starting set, which in turn was equal to 2. So the whole element, the whole exponent becomes 2. Now you've understood, let's say, the trick, which seems almost too effective. Let's put it that way. Who knows if it will really work? And at this point, if we have this equation, then everything becomes much simpler, right? Solving it. The results in principle in general would be more or less the square root of 2. X would be equal to plus or minus the square root of 2. But because of what we said earlier, we must accept only the positive result. So we would have this possible solution, the square root of 2, for this equation. Will it work? Well, let's try substituting it. So let's go and calculate a verification. And here the computer can be useful to us. A verification, let's go and calculate the square root of 2 raised to the square root of 2, etc., etc., etc. You see that the program is already written, but I already prepared it in the environment here in Thonny, let's say, in this environment. And so let's see how the program works. It initializes two variables, b and a, both to the square root of 2, and then it tries, let's say we stop at 1000, obviously, let's say we can't perform an infinite number of iterations, and we calculate the square root of 2 raised to the power of 2, but then we reassign the result to the a. That's why we have the variable b. The variable b will never be modified. It will always be equal to the square root of 2, while a is modified as it calculates this fraction. Okay? So let's see what happens. Let's run the program and we see that it immediately goes into overflow and exits. So the first conclusion would be that there is something wrong with the reasoning. Actually, there is something wrong, but it's not what we think, in the sense that it's not related to the complexity of the problem, to the infinite series of exponentiations to the power. The problem is something else, another problem that is also interesting. And we performed left associativity. That is, we started calculating the square root of 2. We raised the result to the square root of 2, and so on and so forth. However, there is no law that tells us we must necessarily use left associativity. We could also try right associativity. And what would that mean? That we calculate one of the exponents. Keep in mind that we are calculating a finite number of steps anyway, so the last step exists. It's not an infinite series, it's a finite series. So we calculate the square root of 2, and then based on this, we calculate the square root of 2 raised to this, but we consider it as an exponent. We don't consider it as a base. It's a possibility. This should also be explored. So what needs to be done simply in the end in the code, a minimal change, but one that has a certain significance, is to use the variable that is not modified for the base and the other one instead for the exponent. We calculate the exponent from right to left, always using the same base. And we see that in reality, there is an apparent convergence to 2. I am truly sorry for the unexpected interruption that just occurred. I ran into a very small technical problem that needed my immediate attention, but I have resolved it now. Thank you so much for your patience while I sorted that out, and I will resume the presentation immediately from where we left off. So, as we analyzed the data, we saw that within this specific result, we were able to observe a clear and consistent convergence to the value of 2, which confirms our initial expectations. So, returning to our previous discussion regarding the specific problem of right associativity, we might initially be inclined to think that this particular approach we used actually works correctly. However, we should take a moment to consider if that is truly the case. Actually, I'll tell you right away, it's not true, because if we try, instead of putting 2, we put another number, in particular 3, for example, or in any case, a larger number. Let's see. And then we verify. We see that the cube root of 3 raised to itself to infinity does not converge to 3. So we see that in the end, this system is not sufficient. It is not, let's say, the reasoning we made certainly does not hold in general. Well, we can say this. If we really stop to think about it, what is it that makes all of this so interesting? We have come to understand that when we are dealing with infinite sets, we must be extremely careful in equating them or considering them to be equal. This is because infinity, by its very nature, possesses such unique and particular characteristics that it simply does not allow us, in any general or straightforward way, to establish this specific type of equality that we might otherwise assume. A similar problem that I want to refer you to if you want to learn something in this field is a famous false proof by the Indian mathematician Ramanujan, who at a certain point proved that the sum of integers was negative 1/12. Now, how can a sum of positive integers become negative? It is obvious that there was a problem in the proof. However, this problem, which was similar to the one I told you about regarding the issues that concern, let's say, associativity and infinity, This problem was actually very difficult to find, which is why this proof gave even mathematicians a hard time. In the end, then, did we learn anything? Yes, we learned that we must be careful about things we take for granted, in this case, associativity on the right and left, and we must be careful with the use of infinite sets, which sometimes seem easy to us. But in reality, they must be handled with extreme care. Okay? Goodbye. See you in the next video.